and welcome to my talk titled Towards Responsible Electronics, the GreenOMorph project. Okay. I'm from the research institute UNM Research, which has some 500 employees, is owned by the provincial governments in Austria and distributed about 6 locations. I'm in Weiz in Styria, and and 2 out of 7 research units, like materials and life, are involved in this project, and I'm from materials. Right, so to give you an outline, I will introduce you a bit to the environmental impact of electronics today, and then show you our basic approach, which is organic electronics, and then the GreenOMorph approach in responsible electronics, so the approach of our project. And also the manufacture from manufacture to end of life, starting at materials, processes, devices, and recycling. I will show you the plans of the project and some examples of what has been done in the past. So cellulose, dielectric, edible electronics, additive manufacture of electrodes, and also something about neuromorphic computing. And then I will summarize all these ambitions and show you shortly the consortium and how this is funded. Right. So I gave a talk to the general public half a year ago in German, and this the title of that talk summarizes or is a sort of a motto of this project. So in one sentence or one question, how can the environmental impact of the production of electronic devices be radically reduced, and what role should Europe play in there? So we need and we want electronics because they provide us with enhanced knowledge, enhanced control, better communication facilities, and very good entertainment. So electronics enables what we call a good life today. And at the same time, the electronics destroys the environment mainly through the consumption of resources and the associated waste. Its harmfulness during production to humans and the environment. And last but not least, it increases the European dependency on other regions of the world, mainly through the critical materials. And this was, so Adam showed this very nicely, how we depend on others through our choice of materials. So at the same time as it enables a good life, it also endangers this good life. This is, in brief, what the producing of silicon chips does to the environment. So it overtook the car producers even already in 2016 with respect to the greenhouse gas emissions. And at the example of an Apple personal computer, this is mainly because of the manufacturing, so 3/4 of it by manufacturing, and half of this is attributed to the manufacturing of IC or the chips. And the tendency is increasing on front end and middle and back end of the production lines. So what can we do about it? And a very basic approach is to substitute silicon with alternative materials that are thin, light, flexible, bio-based, harmless, and provided by green chemistry, ideally. And so we try to switch to carbon-based, or in other words, to organic electronics. And we also want to substitute the fab processes which require extreme conditions. So we want to go over to a low temperature and without vacuum processes that consume much less energy and water and no toxic gases at all. And so we want to arrive at an additive manufacture, and this is mainly printing. And this is not so technical, but sort of political. So we want to change our attitude to fit for purpose from a performance at any cost attitude. So we will arrive at simpler circuits and products at lower consumption of resources. And this could be realized in our vision, at least, that this is achieved by organic printed devices. And we want to manufacture, above all, more sustainable electronic products by optimized exactly for the purpose, to summarize it in one sentence. Well, so to address this, the EU put a Pathfinder challenge called Responsible Electronics, with the main requirements to maintain or even enhance a digital society in Europe, and then radically reduce the environmental impact. So the main goals is to reduce the energy consumption and to reduce the use of forever chemicals, so the PFAS, and also at the same time we want to enhance the industrial autonomy of Europe, and that is by reducing the consumption of critical raw materials. Also in the talk of Adam, this was very nicely illustrated. And so we were quite proud because we were among the lucky 9 out of 127 submissions who were funded, and so we got an EU project called Green Materials for Neuromorphic Signal Processing by Organic Synaptic Transistors, with the nice acronym GreenOMorph. And this should address the whole life cycle from employing sustainable materials to using sustainable processes, and also care about the recycling. And here are the 6 logos of the partners. So it's a rather small consortium for these ambitious goals. And so the basic approach of this project is using organic electronics. And so why this? When we compare it, on the plus side for organic electronics is performance-wise, it's this use of versatile substrates as compared to silicon only in the conventional silicon electronics. It's lightweight, comparably, and it's flexible, stretchable, or even foldable instead of the rigid chips of the silicon electronics. Economically, we could produce this in large areas of square kilometers, even if we go roll-to-roll manufacture, and this would be at low cost. And also extremely in roll-to-roll manufacture, we could achieve a very high throughput. And concerning the environmental impact, the process temperatures could be, or must be, in the case of polymers, drastically reduced to below 150 degrees C, as compared to the high process temperatures. For instance, the oxidization in silicon would need more than 1000 degrees C. Also, additive patterning is possible in organic electronics, whereas in silicon electronics, we have subtractive patterning only. And on the downside of this kind of electronics, this is the speed and the area consumption, where we are many orders of magnitudes off the silicon chips. But in these targeted applications and which are emerging, which is edge computing and the associated Internet of Things, the performance could be sufficient for many applications in mass. Right, so maybe you know it, but the people from the street may ask, organic electronics, does this exist at all? Never heard of it. It exists in research and development for, say, 30 years. So here's one example we made up by ourselves. It's a tactile active matrix sensor. In the backplane used organic electronics. And in this box on the bottom, you see that it was researched in many different application areas. And only recently it made it out of research and development into industries, as FlexEnable provided a backplane layer for an active matrix e-paper display by ledger stacks. And very recently, you are able to just buy organic electronics as a consumer. So for instance, those flexible displays you can buy for not so little money, but it's only the market entry and the beginning. Okay, so you would say, when you have seen this, you might ask yourself, can this be more environmentally friendly? So especially in English, if you name it organic electronics, it sounds very nice, but you could, with equal rights, you could name it plastic electronics, which sounds quite nasty nowadays. And so you might ask yourself, does this contribute to more waste, even more plastic waste? Are we going from bad to worse? But the goal of our project is to clearly say no. Just in the contrary, we will be very environmentally friendly. And the project is guided by the safe and sustainable by design principle from the beginning. Materials, processes, and devices are analyzed by LCA and also SLCA. And the importance of this is reflected by nearly 20% of the staff effort of the project are dedicated to our work package 1 sustainability assessment. So let's start at materials. Our specific objectives comprise the development of a green ferroelectric material consisting of a biopolymer, which is a very challenging task. And also a big objective is to have sustainable organic semiconductors of P and N type, but also all materials that are needed for organic thin film transistors and organic electrochemical transistors. And so let me show you an example of the past. It's quite some time ago when we tried cellulose as a gate dielectric for OTFDs. And this worked out quite nicely. So with the sort of precursor DMSC, we had a nice performance. At that time, pentacene was the the organic semiconductor of choice, and it showed a reasonable mobility for this material. So it was as good on the DMSC as it was on other dielectrics. And then this was regenerated to cellulose, because this was the goal of the demonstration, that this natural material would also work, and we could prove that it works. So this DMSC is quite a nasty material, and this was a demonstration, but at that time you could not make a reasonable thin and electrically dense layer out of cellulose directly. And another proof that this worked nicely was this organic complementary inverter with a very nice symmetry and a noise margin of 92, and that cellulose still 82%, and a gain of 500, and that cellulose still 50. And so this was a result of quite early days. And now I show you a second example of a recent research. Our partners from IIT of Italy, they are researching edible electronics, and this would be the ultimate proof of safe and non-toxic organic materials, just to show that they are edible, or using food-related materials for the electronics. And beyond that, the vision is that you could use it and ingest, for instance, diagnostic devices, or on the other hand, you could use it for monitoring quality and non-toxicity of food. And as an example, I show you here a fully edible electrolyte-gated field effects transistor. So as a substrate, they used ethyl cellulose, which is edible in itself. And then they used, for the electrodes, they used edible versions of silver and gold. And interestingly, for the as a semiconductor, they used copper phthalocyanine, which is a known N-type semiconductor, and this is an ingredient of toothpaste. So you would swallow toothpaste by accident, and so it must be tolerable by the human body. And as the electrolyte, they used chitosan, which is a nutrient supplement. And so they rendered the whole device edible. And then they did a careful analysis of the ADI, which is the allowed daily ingestion. And they arrived at the conclusion that the 10,000 transistors would fit in this average daily ingestion. So you could use quite complex ICs and circuits, and you could ingest them for instance, for diagnosis purposes. Right, so now we have sustainable materials, and in this project, we are aiming at strictly additive manufacture. So we want to manufacture sensors, electronics, and also this synaptic device additively. So no photolith, no etching, no lift-off, no strip, no clean room. So this is a completely different world as compared to the silicon And as additive processes, we are aiming at printing, plate coating, imprint, and a special printing process by our Finnish partners, VTT, which is the reverse offset printing. And as an example that additive manufacturing of electrodes is possible, I show you, I show you a nano-imprint lithography patterned electrodes for polymer sensors, but these electrodes could be used for OTFDs as well. So this is a paper of 2020, and the background of all this is that we have a nice sensor technology called Isoflex. This is based on PVDF DRFE, a copolymer which unfortunately is a PFAS. So we are also in this project, we try to replace this by a biopolymer. But here I want to show you this electrode manufacture. So this was the motivation why they wanted to introduce the lateral electrodes, but this is not so important for this transistor electrodes. But here would be a sort of a semi-additive fabrication by an electroplating process. And so it would start by a subtractive process by photolitho and lift off of a very thin seed layer that just needs to be conductive. And then the thick layer would be added by electroplating, which is could be regarded as additive, and then the PVDF would be printed on top. So this is semi-additive. This is good, but not good enough for our project with its radical approach. And here is a fully additive fabrication. So hot embossing is a variant of the nano-imprint lithography. And we imprinted the PVDF by hot embossing and created these microchannels in the PVDF. Those were activated by ozone, because then the conductive ink would be deposited at the edge of these channels, and the channels would be formed by self-wetting or, say, capillary action. And on top, an insulating layer would be printed, and so we have a pure additive manufacture of metal electrodes. So this video shows how this goes in principle. You see this spill on top, so it's not a perfect one, but it shows nicely how the idea of this additive manufacturing by capillary action. We will not use exactly this process in the project, but we will also use nano-imprint lithography combined with other additive deposition methods. And so we arrive at this, on the bottom right, you see these channels. They are not really filled by the metal, but they are metallized. And this was sufficient that the sensor works equally well as the vertical electrode sensor. So here in the middle, you see that there is the sensitivity is reduced, but the quality of the signal is the same. So there is no erroneous detection or anything, right? So we are able to have green or sustainable materials, and we have additive processes. And now we want to, with these, we want to create neuromorphic devices. And this would be done by the TU Eindhoven, our partner. And so a few words about neuromorphic computing. This is neuromorphic means that memory and processing happen in the same place or in the same device, as is the case in humans or animals' brains and also our bodies. And it is sort of an opposite of classical von Neumann computing, where information needs to be sent between memory and processors requiring lots of traffic. So potentially this is extremely energy efficient. And so we decided to create a neuromorphic device. Also in this project, we will make neuromorphic devices instead of simulating neuronal behavior by von Neumann computers, because there you would lose all the energy advantage. And so we will create a sensor nerve synapse system, and our demonstrator is this organic artificial sensory neuron you see depicted on the left. Yeah. And ultimately, we want to make a small array of these of these neurons and apply it in an array for a tactile pattern recognition. Right, to give you an example of a neuromorphic organic device, I show you some contents of a paper of the TU Eindhoven, our project partner. So there's a 3-terminal synapse you could create by it basically is an electrochemical transistor. So by a gate you can inject charges which would then decrease the conductivity of the channel, simply speaking. So you see this NOD, as they call it, during programming. You can look up the details in the paper. It's not so easy to explain here in short. But basically what it does is that charge pulses to the gate would influence the channel conductance. And this is very linear, which has the advantage that so-called blind programming is possible then in these neuronal applications. Right, and an important parameter in neuromorphic computing also is the plasticity and the associated retention time. And they modeled it by this exponential behavior and fitted it and extracted an retention time of 3 hours for the system. And then 3 of these neuromorphic devices were arranged to create a 3x3 neuronal kernel. And this was applied to the convolution experiment, and there they used a 128 times 64 pixel representation of their logo, and you see on the left the original, and then they programmed the kernel for a blurring filter, which worked, as you can see in the center of these 3 logos, and also the edge filtering worked, as you see in this darkened picture on the right. Also, they extracted an energy efficiency of 26 tera operations per second per watt, which is considered as an excellent efficiency. So we would create a neuromorphic device by using sustainable materials and additive processes. And it's a layered technology, so we have only tens of nanometers thin layers, and we have substrates which can be as thin as 1 micrometer, but a maximum 100 micrometers thick. Still, we want to demonstrate experimentally that we can recycle the metals and render the substrates reusable. So with only 1% contaminants, and the recovery of the metals our goal is 99%. And as said in the beginning, the safe and sustained by design principle and the LCAs are carried out throughout the project. So this is then the total picture of this ambition of the project. So it's time to summarize what we want to show. So many promises. So in 4 years, maybe you can ask me what we really achieved. But it's quite rare that in an EU call you find the word radical. So our approaches are quite radical, and they are quite low DRL. So we are quite at the start. So the goals are ambitious. It's 0 critical raw materials. And so even we avoid aluminium. And I learned by this talk before that aluminium is a critical material. Though it is I saw it's the 3rd most abundant material in the world, but still it's not so easily, so the supply is not so easy in Europe. And the PFAS should be eliminated, so no fluorine at all in the products we have. So as the project is set up in the beginning at least, so we have no halogenated solvents and no fluorinated gases. And as mentioned, we want to replace even our well-working PVDF by biopolymer. And toxic materials in the product, we have 0, no halogenated solvents as mentioned. And the reduction of greenhouse gases is through the use of neuromorphic organic devices in suitable applications. This is a huge reduction. And in the fabrication was a difficult estimation. So we guessed that we would need less energy by 2/3, but as these per function, which is important there. So the very minute areas of the silicon electronics and the huge areas of the organic electronics make it quite difficult to compare, but still this was the best of our knowledge, our guess of energy saving in the fabrication. And yes, recycling, I mentioned it, just 99% of the metals and reuse of the substrates, so which would leave a minute amount of materials for disposal. And also the solvents we aim to recycle by 90%, and the E factor, which is the fraction of the waste over the material in the product, we want to improve by a factor of 10. When it comes to performance, these soft performance parameters are good. So it's flexible, lightweight, thin, and therefore it's easy to integrate, even in the human body. So it's this. These are the pluses, but on the downside we have a mobility of 1 square centimeter over volt seconds and frequencies in the kilohertz range and channel length of 5 microns. So if a silicon manufacturer sees this, this is he would say this is poor, but as we said, in these edge computing applications, the integrability would weigh more than the performance in terms of speed. And yes, this is the project. We are grateful, of course, for this funding by the EU. It will last 4.5 years, so still 4 years to go. And we got 4 million euros of funding and 404 person months of staff effort. 6 partners, so it's 4 institutes, 2 universities from Austria, Italy, France, the Netherlands, and Finland. So no, as I said, it's low TRL, so for us unusual, quite close to basic research, so there is no company in the consortium. Also unusual to us is to have this portfolio activities. So all the 9 projects that were granted in the call are encouraged to work together to look for synergies. And this is this portfolio of 9 projects. So if you look up the project homepage, you can also get there. So budget, we get a large fraction because we're in by 2 institutes, and we are also the coordinators. And I'm quite proud that we got together this consortium, and you see most of the folks that work on the project you see on this photo, which was taken at the kickoff meeting in Graz. And here you have all the contact details, and with this I want to thank you for your attention.
Thank you very much, Herbert. It was a really interesting talk and project, the GreenOMorph. So from the audience, I'd like to know if there exists any questions or doubt to Herbert about the project.
I have a question.
Yes, please.
So in the last part of your presentation, you said that one of the requirements on the retention was about 10 minutes, right?
In this neuromorph,
Yes.
I see, yeah.
On the performance. So what kind of applications are you planning to try for, like spiking neural networks?
Yeah, it's spiking electronics, and so I'm on thin ice. I'm not an expert in neuromorphic computing, so I might be a beginner, but I try to answer. So we want to use this for a tactile pattern recognition. So if I can show you, yes, so this is a sketch. So this consists of 3 parts. We have a sensor, a electromechanical transducer, in fact, which would transduce mechanical tactile inputs to electrical signal, and then we have the signal conditioning circuits, which would generate the spikes, and then we have this synaptic device here, which would be either a electrochemical transistor or a ferroelectric transistor. So we will make a ferroelectric transistor. And for this purpose, I think this retention time is sufficient. So I'm not 100% sure if this specification would be sufficient for this, but to be honest, I took this over from our agreement and our specifications in there.
Thank you.
Yeah, I have another question. I saw that in your neuromorphic device that you showed, you used the active layer P.PSS. So since you want 0 toxic material, so this PSS is something that is quite critical in terms of toxicity and the LCA. So in the project, you planned to change your active layer of this semiconductor?
Yes, yeah. Okay. Yeah, this was so we are quite at the beginning of this project. It was quite a lot of advertising, and I have to admit, and then lots of promises. And yeah, so just just recently we had a list of critical materials, and we also analyzed the PSS, and it should. So the electrochemical transistors in the project should be different from this one.
Yeah, if it's just the PEDOT, I think is not a big issue. The problem is the PSS. But of course, it change a lot of properties in the active layer if you don't have the PSS layer.
Yeah, so this is done by IIT, and they have lots of experience in electrochemical transistors. So we know this PSS, but they know other ones as well.
Yeah, and in the project, you also plan to use like sustainable substrates, like you mentioned, cellulose or even ethyl cellulose in roll-to-roll protection, or just at low scale?
Yeah. Oh no, we are quite far off roll-to-roll
Okay.
production here. So this is the roll-to-roll production and we have lots of experience in it. This is the potential when you use polymers and organic electronics, so because they're flexible and you can use a polymer substrate right away.
Yeah, I'll just ask because I know that you have the facilities for it, like in the pilot scale and roll to roll. And I didn't know if one of the partners responsible to do like a roll with a sustainable substrate to then for you to use in the project, or just a curiosity.
Yeah.
Okay, so thank you very much, Herbert, for your interesting talk. So our next speaker